Students, we are back at chapter 5, and in this lecture I want to talk about some general reactions that you guys will see and do a little bit more balancing equations. So the first type of reaction that you guys might see is called a combination reaction. And so we take two substances, and we react them together to form a single product. So you can see with the example here, we take hydrogen and we react it with oxygen and we make water. Now the other way that you guys can write water is HOH. And that might help you when you're doing balancing equations to write water that way. So just note that you can do that. Here's a funny little comic here saying make your own bottled water, get a couple of hydrogens and an oxygen, combine them together. And then the next reaction is called a decomposition reaction. And in a decomposition reaction, we have a single substance and it breaks into two or more products. And this is the opposite of a combination reaction. So if we were looking at the opposite of combining hydrogen and oxygen together, we would see that we can take water and break it down into hydrogen and oxygen. Now you have the coefficient of 2 in front of the water and the hydrogen, and you have a coefficient of 1 in front of the oxygen, and that balances that equation. So then we have 4 hydrogens on both sides and we have 2 oxygens on both sides. And remember, that's the conservation of matter, or the conservation of mass, which says we have to have the same number of each element on each side, and we have to have the same mass on each side. So how might I do this reaction right here? Break water down into hydrogen and oxygen. Well, I have a little picture here for you guys, and this is called electrolysis. So what we would do is we'd put some water in here, and we'd run an electric current through the water, and what we'd find is that at the anode, which is right here, we would form oxygen, and the oxygen, because it's gas, would form bubbles, and they would go up here into this balloon. And over at the cathode, which is right here, we would form hydrogen, which is also a gas, so we would see bubbles forming. And those two would go on up to the top here and into this balloon. And that's how we would see that we were doing this reaction. We'd have the formation of these two gases. Now, if you look at the hydrogen balloon, it's bigger than the oxygen balloon, and that's because for every one oxygen molecule we form 2 hydrogen molecules. So that should make sense to you guys why the hydrogen balloon is bigger. Now, notice these funky equations down here at the bottom, which include electrons in them, and we haven't seen anything. We will get there when we talk about a reaction called a redox reaction. So don't worry about that till we get there. Just know that we can decompose water into oxygen and hydrogen gas. The next type of reaction that you will see is called a single replacement reaction. It's also called a single displacement reaction. And what happens in the single replacement reaction is we have one element and it's going to react with a compound, and the element is gonna kick one part of the compound out and it's gonna bond with the other part of it. So if you look down at the general single replacement reaction down here, you can see that A comes along and it says to X right there, hey, get out of here, I like Z. And X is unhappy, but it leaves, and then A and Z form a happy couple, and then X is on its own. So we replaced one thing, so single replacement. Now, the reaction right here that we see is that sodium metal, which is a soft metal, will react with liquid water and form sodium hydroxide and hydrogen gas. Now, if we rewrite water the other way that we talked about, HOH, you can see that sodium is coming in here and it's kicking out the hydrogen and it's grabbing the OH to form NaOH. And we have to have that happen 2 times so that 2 hydrogens get kicked out and they can form hydrogen gas. Now, sodium metal is right here on this slide, and we can see that it is a soft, shiny metal, and the person who's holding that sodium is wearing gloves because on the surface of our skin we have water, and we don't want a reaction happening on the surface of our skin because not only does this reaction give off heat, but it gives us a flammable gas, and hydrogen is the flammable gas. So what happens when you have a reaction that gives off heat next to a flammable gas is that you get lots of sparks flying. So if we put a little piece of sodium metal into a sink that had some water in it, it would buzz around and go bzzz and give off little sparks, and it's kind of a neat little reaction. Okay, so the next reaction we have is a double replacement. So this means that you have 2 compounds and they're going to switch partners. So you can see that A gets together with Z and X gets together with D, and they form new partnerships. This is also called double displacement, or it's called an exchange reaction. You'll see it called all 3 of those. Now, if we look at the reaction of lead nitrate here, you can see that lead is going to get rid of its nitrates, and it's going to get together with the iodide over here and form lead iodide. And that means that we have potassium and nitrate getting together to form potassium nitrate. Now, what's driving this reaction is the formation of this solid. We'll also call it a precipitate. And that is sometimes abbreviated PPT. So if you see precipitate or PPT, it means that you're forming a solid. Now the solid doesn't always sink to the bottom. Sometimes it kind of floats around in the solution. It just depends on its density. And if we notice something else about the reaction, that we see AQ, 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 what that is telling us is that we took this compound and dissolved it in water, and we took this compound and dissolved it in water, and they did their reaction, formed the solid, but the other product is still dissolved in water, which means that it's still floating around in its ionic form. So we have the potassium ions, which have a charge of +1, and our polyatomic ion nitrate, which has a charge of -1, still floating around in the solution. Now I have a picture of this on the next slide. And it shows you that in the first beaker, this one right here in that person's hand, that we have potassium iodide dissolved in water. So you guys can see that floating in water are K plus and I minus. And then in this beaker right here, we have dissolved lead nitrate. And we can see that we have lead, which has a charge of +2, and we have nitrate floating around. If you want to go ahead and draw another nitrate so it makes more sense that it was PbNO3 with parentheses 2, so 2 nitrates for every lead, you can go ahead and do that, and that would make sense because you have -1 and -1, and that would have to get together with a +2 in order to make a net charge of 0. But anyways, when we put these two things together, the lead right here is going to find 2 iodides, and it's going to form PbI2, and that's a solid. And you guys can see it forms this lovely yellow solid here. And if you give it a little bit of time, it will settle out on the bottom. Now, you can see that the potassium nitrate still says AQ right there. So that means that we still have potassium K plus, that's a K plus floating around, and we still have nitrate floating around in the solution. And what gives us that information is that AQ right there. It says it's still dissolved in the solution. But the solid, the S on the lead 2 iodide right there is telling us that it forms a precipitate. So that's what that looks like. And the next type of reaction we're going to talk about is a combustion reaction. Now, a combustion reaction, what we'll see is that we're going to take a hydrocarbon. So that is a molecule made up of carbons and hydrogens. And we're going to react it with oxygen. And our products are carbon dioxide and water. Now, the hydrocarbon that we have right here, it has a single carbon and it has 4 hydrogens around it. And this is called methane. There are lots of hydrocarbons. In natural gas, we have a combination of methane and ethane. And natural gas is the gas that we use in our homes for our water heaters, if they're gas water heaters, for our stoves, if we have gas stoves, if we have gas dryers. This is what we use. Ethane, the other component of natural gas, is C2H6. And the Lewis structure for that looks like this. We've got 2 carbons bonded to each other and hydrogens all around. Now, if we go up to 3 carbons, we'd have C3H8, and that's a hydrocarbon you guys have probably heard of before. That's called propane, and propane we use in our barbecues. If we go up to C4, we'd have C4H10, and that is butane. Butane is a gas that we use in cigarette lighters. Now, it looks like a liquid because it's pressurized in the cigarette lighter, and it's kind of at the border between gas and liquid anyways. But anyways, when we have a combustion reaction, this gives off a lot of heat. And we can see that with our eyes when we're burning propane on our barbecue, and we can we can see the light energy that it gives off with our eyeballs, and we can feel the heat energy that it gives off because we can feel the heat. So that's a combustion reaction. Hydrocarbon, oxygen, carbon dioxide, and water. And then sometimes we'll see plus E, and that's for energy. And again, we're getting light and heat energy off of it. Or sometimes we'll not see the light portion of it, and you'll see just plus heat. That's a couple of ways that you'll see this reaction written. All right, so let's go to some problems. So we're going to balance the equations here, and we're going to identify which type of reaction we have. Now, number one, we've got C3H8. And we're reacting it with oxygen, and we're getting carbon dioxide and water. So we've got propane plus oxygen, which gives us carbon dioxide and water. And that should be like ding, ding, ding in your head. That's a combustion reaction. We just talked about that. So we'll go ahead and write combustion here. Now, on the reactant side, we've got 3 carbons from our propane. And on the product side, we just have 1 carbon from that carbon dioxide. So we need to have an equal number of carbons on both sides. So what number will we put next to carbon dioxide? 3. That's right, because we want 3 carbons on both sides. Now we move on to hydrogen, and in propane we have 8 hydrogens. Now the molecule that's giving us hydrogen on the product side is water, and each water gives us 2 hydrogens. We need to have 8 on each side. So how many waters do you need in order to have 8 hydrogen atoms on the product side? 4. All right, so we move on to oxygen, and that's generally the order that we do the balancing for combustion reactions in. We go carbon, hydrogen, oxygen. And the 3 carbon dioxides that we have, that gives us how many oxygens? We have 3 times 2 because every carbon dioxide has 2 oxygens. That's 6 oxygens. So we have 6 oxygens here, and we've got 4 waters, and each water brings along with it 1 oxygen. So 4 times 1, that's 4 oxygens. So we have a total of 10 oxygens on the product side. Now over on the reactant side, our oxygens, they come as a molecule. So that looks like this. They come in pairs. So in order to have 10 individual oxygen atoms, how many oxygen molecules do you need? 5, because 5 times 2 makes 10. So we have 3 carbon atoms on each side, we have 8 hydrogens on each side, and we have 10 oxygens. Okay, number 2, we've got barium chloride and we've got sodium sulfate, and that's going to make for us barium sulfate and sodium chloride. Now what I want you guys to notice is you've got a lot of AQ, AQ, AQ here, and you have a formation of a solid right there. So that should indicate to us that this is a double replacement, also called double displacement, also called exchange. So we have our cations exchanging their anions with other cations. So we can see here that our barium is going to pick up sulfate, and our sodium is going to pick up a chloride. So they exchange partners. Now on each side we have a barium. We have 1 and 1, so we're okay there. And then on the reactant side, when we move on to chlorine, we can see that we've got 2 chlorines on the reactant side, but we only have 1 on the product side. So how many sodium chlorides do I need in order to have 2 chlorides, or 2 chlorines? That's 2. Now, if we go on to the next ion, or the next atom, we can see it's sodium. We have 2 sodiums on the reactant side, and we have 2 sodium chlorides on the product side, and each sodium chloride brings with it 1 sodium. So if we have 2 sodium chlorides, we have 2 sodiums. So we're balanced there with our sodiums. Now we're going to move on to the sulfurs and the oxygens. Now the sulfurs and the oxygens, I want you guys to keep those together because that is the polyatomic ion sulfate. And when you're balancing equations, it tends to be easier if you just keep your polyatomic ions together as a package and you say, I've got 1 sulfate on my reactant side and I've got 1 sulfate on my product side, so I'm balanced. Now, it looks like everything's balanced here. We've got 1 barium on each side, 2 chlorines on each side, 2 sodiums on each side, and 1 sulfate on each side. So you guys can draw the ones in the coefficient lines if you need to, but remember you don't have to if it's a 1. All right, number 3, we've got iron reacting with water, and we're gonna form iron oxide here and hydrogen gas. Now on the reactant side, we have how many irons? We have 1. And over on the product side, we have how many? 3. So that means we need how many irons on the reactant side? 3, because we need to balance our equation. So iron is going to come on over to water and steal water's oxygen, but it needs to do that 4 times, and it needs to get together with a group of 3 irons, and those 3 irons will go after 4 waters and get together and make this product. So don't get confused by the 3s and the 4s there. What we're still doing is we are replacing the hydrogen with an iron. So what we have here is we have a single replacement. Okay, so back to balancing. We've got 3 irons on each side, and if we move on to oxygen, we can see that we've got 1 oxygen from that single water that we have, and we have 4 oxygens in our iron oxide. So how many waters do we need in order to have 4 oxygens on the reactant side? 4. Okay, so that leaves us with hydrogens, and we have 4 waters, and each water has 2 hydrogens. So we've got 4 times 2 there. So we've got 8 hydrogens. Now on the product side, the hydrogens come in pairs because it's a hydrogen molecule, an H2. And in order to have 8 hydrogens on the product side, we need to also multiply H2 by 4 like we did with our water. So then we have 3, 4, 1, and 4. So 3 irons on each side. We've got 8 hydrogens on each side and 4 oxygens on each side. Now, number 4, we've got platinum reacting with fluorine to make PTF4. So we have two things reacting to make a single product. So what kind of reaction is that? That's combination. Okay, so on the reactant side we have 1 platinum, and on the product side we have 1 platinum, so we're good there. On the reactant side we have 2 fluorines, and on the product side we've got 4 fluorines. So what do I need to do on the reactant side to balance our fluorines? I need to put what coefficient right there? A 2. So I've got 1 platinum on each side, and I've got 4 fluorines on each side. All right, number 5, we have H3BO3, and that's gonna bust up into 2 products, B2O3 and H2O. So when we have one reactant decomposing into 2 or more products, what kind of reaction is that? That's decomposition. Okay, so back to balancing this. We've got 3 hydrogens on the reactant side, and we have 2 hydrogens on the product side. Now, when we have 2s and 3s together, we need to go where? To 6, that's right. So what do we multiply 3 by to get 6? 2. And what do we multiply 2 by to get 6? 3. Okay, so now we have 6 hydrogens on both sides. How many oxygens do we have on both sides? Well, we've got 2 times 3 here, so we've got 6. And then from the product side, we've got 3 here because we have 1 B2O3. And then we've got 3 waters, which each bring with them 1 oxygen. So we have 3 oxygens from the water. And 3 oxygens plus 3 oxygens equals 6 oxygens on the product side. So we have 6 oxygens on the reactant side and 6 oxygens on the product side. So we're good with oxygens. And then we have 2 H3BO3s. Each one of them brings with it 1 boron. So we've got 2 borons on the reactant side, and in B2O3 we've got 2 borons. So we are balanced here. Now again, you do not have to write the 1 in front of B2O3, but if you want to, go right ahead. All right, for number 6, we have C4H10, which is butane. And it's going to react with oxygen to form carbon dioxide and water. And you'll also see light and feel heat. So that gives us what kind of reaction? Combustion. So combustion, you guys, is always going to give us carbon dioxide and water, and it's going to be a hydrocarbon reacting with oxygen. Now, for combustion reactions, we balance carbons, then hydrogens, then oxygens. So we can see on the reactant side, we've got 4 carbons from the butane. So how many carbon dioxides do we need? 4. All right. Then we have 10 hydrogens. And on the product side, our waters give us 2 hydrogens each. So how many waters do we need? 5, that's right, because 5 times 2 is 10. Now on the product side, we have 4 times 2, which is 8 oxygens, and we have 5 times 1, which is 5 oxygens. And that's going to give us 13 oxygens. Now this is a problem because that's an odd number of oxygens, and on our reactant side the oxygens come in twos. That's the oxygen molecule, and you can't split that up. So what we're going to do for this one is what we practiced in the last video, which is doubling the coefficients. So in order to get 13 oxygens on each side, you would have to multiply 2 by what number? 6.5. So 6.5 times 2 would be 13. But again, you can't have 6.5 oxygen molecules. You can't just chop that oxygen apart. So we double our coefficients. So 1 times 2 is 2, and 6.5 times 2 is 13. Hi, kitty cat. And 4 times 2 is 8. And 5 times 2 is 10. And you're balanced there. Yay! Okay, so the next type of reaction that I need to talk about is a little bit weird, but it's called a redox reaction. And this is a combination of oxidation and reduction. These things always happen together. And this is a reaction where you have a transfer of electrons. And it goes from one reactant to the other reactant to give you a product. So we can see in the reaction below that we have reactant A. And right here it's telling you it's got a charge of 0, so it's neutral, with reactant B. And up here it's telling you that it's neutral. And what's happening is that A is transferring one of its electrons. So we have an electron right there. It's transferring it over to B. So what we end up with is that A lost one of its electrons. So now it has one more proton than it has electrons. So it ends up with a positive charge. And we have B that has gained an electron. It has gained a negative charge. So it has one more electron than it has protons. Protons are positively charged. So it ends up with a negative charge. Now, if you lose an electron, you are oxidized. So that's called oxidation. If you gain an electron, that's called reduction. You are reduced, okay? So we have reduction right there. And again, these always go together because if somebody's losing an electron, somebody else is gaining an electron. So we always have oxidation and reduction together, so that's why it's nicknamed redox. So looking at an example of this type of reaction, we'll see here that we have sodium metal, and that's a solid, and it's reacting with chlorine gas. And chlorine is a green toxic gas, and that's going to make sodium chloride. And we have a very reactive metal, sodium, reacting with a green toxic gas to make sodium chloride, which is our favorite solid because we like to put it all over our food, and it's such a lovely compound. Now, if we were to balance this, we would see that we needed 2 chlorines on the product side because we have 2 chlorines from the chlorine molecule, and you don't chop that apart. So we'd put a 2 there. But that means now we have 2 sodiums from our 2 sodium chlorides, so we'd have to put a 2 over there. So if we were being sticklers about balancing the equation, that's what it would look like. Now going back up to the top here to see where the electrons are going, the sodium metal is right here in its natural state. So it's going to have a charge of 0, and the chlorine that's drawn there is also going to have a charge of 0, and we're assuming that that chlorine right there is one of the chlorines from a Cl2 right there. And the sodium will lose its electron and give it to the chlorine. So we have oxidation of sodium. So because sodium loses one of its negative charges, one of its electrons, now it has one more proton than it has electrons, so it goes to a positive 1 charge. And because the chlorine picks up an electron, it gains an electron, it is reduced, so we have reduction of chlorine there. And now it has one extra electron, so it has one more negative charge than it has positive charges, so it has a charge of -1, so then it's a chloride. So then we end up with that happening 2 times because we've got 2 sodiums, and each one of those sodiums is transferring an electron to these 2 chlorines, and then we're going to get 2 sodium chlorides there. So we have oxidation and reduction happening together. So we have a redox reaction right here. Now, redox reactions can be also one of the other categories. So here we have sodium reacting with chlorine to form sodium chlorides. So we could consider this to be combination also, and that happens quite often. Now this slide right here, it's showing us the same thing that we saw in the last slide, except it's introducing us to the concept of oxidizing agent and reducing agent. Now these definitions kind of seem backwards to some students, but I'll explain it here. So compound A right here, it's giving away its electrons to compound B. So compound A is being oxidized, but because it's giving away its electrons to somebody else and causing somebody else to be reduced, it is called the reducing agent because it is reducing somebody else, but it itself is oxidized. Now, B right here is picking up the electrons from A. So B is being reduced because if you're gathering negatives, you're being reduced. Your charge is being reduced. Like chlorine on our previous slide went from a charge of 0 to a charge of -1. So that number went down. But because it is being reduced and it's stealing electrons from somebody else, it means that it is oxidizing somebody else. So that means it's the oxidizing agent. So if you yourself are being reduced, you're oxidizing somebody else, so you're the oxidizing agent. So again, the oxidizing agent is the compound that's oxidizing somebody else, but it itself is being reduced. And the reducing agent is the compound that's reducing somebody else, but it itself is oxidized. Now, this right here, oil rig, this is just a way to remember oxidation and reduction. So we have oxidation is loss. And it's loss of what? Electrons. I should put of electrons there. And reduction. Reduction is gain of what? Of of electrons. Okay, so where we will see that is another reaction with chlorine here. When chlorine reacts with potassium, it's going to form potassium chloride. Now, this is analogous to the reaction with sodium, and potassium and sodium are in the same group on the periodic table, so that makes sense. They have the same reactivity. So looking at this slide right here, we can see that we have potassium metal, and that has an oxidation state or a charge of 0. And we have chlorine right here, which has a charge or an oxidation state of 0. And we have potassium giving chlorine an electron. So chlorine goes from Cl with a 0 oxidation state to -1. And potassium, because it's giving away its negatives, goes to +1. So we have a couple of potassiums, and they are reacting with a chlorine molecule. And this potassium is giving this chlorine an electron, and this potassium is giving that chlorine an electron. And what we end up with is that and that, which we write as 2KCl. Because remember, when we're writing the formulas, we don't write in the charges there for ionic compounds. We just assume that you know it's there. Okay, so looking at our problems on this slide, the problems are not showing up for me on this slide. That is really weird. Let's see if I go back, and then I go back again. Nope, problems not showing up. Okay, so I guess we're gonna have to do those problems on the next video. And on the next video, we'll also talk about the mole. Okay, see you next time, guys. Bye.